Hello, Assalamu alaikum. My name is Mohammad Baid Khan, and today I'm going to be explaining about my lab 10 task 2, which is about ADC mainly. ADC is analog to digital conversion, and I'll be explaining this code, this task. So, first of all, we start with these headers. Uh, we are defining our crystal speed here, the oscillation speed here, the speed on which our calculations will be done. Then we define our main uh, pins here of the our LCD that we will convert to show our data on here. Then we have our AVR header here that we use and uh, we basically use the input output functions through this library. Then we have our util library, which we use for our delay and other stuff. Then we are including one of our own libraries, which is of the LCD library that we will use to show our data, display our data onto the LCD in Proteus. Here is the library. You can see I have added this library by right clicking on our file name and then going into add and then into existing items. And after that, we have our main function. Uh, and in our main function here, what we have is we have first of all our variable declaration here. We are mainly declaring an array here of unsigned char type, which will hold our ADC strings here that we can call, uh, and these will go from 0 to 1023, which are our maximum steps that our 10-bit ADC can go to. And after that, we have our then we are declaring our inputs and outputs. Here we are declaring our our port F as our input, which is our mainly ADC. Our ADC pins are all in the port F, and we are making that port as our input. So we will be using those ADC pins for input. Then we are declaring our port B and port C as output. Here we will be displaying our data and connecting the control lines of the LCD here. That is why we have our 0xFF and 0x00 here. With the 0x00, we are declaring the input. With the 0xFF, we are declaring the output. After that, we have our ADCSRA, which is our ADC, our control register here. So in here we are giving it the value of 0x87. Now we have to convert this 0x87 into binary, which will be converted as 1000 and then 0111. So here, using this register, we will go and select our prescaler. We will enable our ADC here. Uh, why are we doing this? We are doing this to just turn the ADC on and then convert our analog data into our digital data, and then we will be displaying that on our LCD here. Uh, here we have our data register here, which will simply hold our value. So this 0x87 value will be converted into binary, and then it will go into the register, and accordingly the register will then use those values and do the function accordingly. For in our bit 7, we will have ADEN, which is simply the enable pin of our enable bit of our register here, which will enable the ADC, turn it on. Then we will give the ADSC, we will give it a 0, so it won't start. We will give our ATE, the auto trigger, we will turn it off. We will turn the interrupt flag off here. We will turn our interrupt here, we will turn it off. And then in the prescale section of our ADC, those 2 bits, we will just give it the value 111, sorry, the 3 bits, we will give it the value 111, which will simply, according to the table, it will give the prescaler a value of 128. When we will divide that value by our oscillation speed, which is 16 megahertz, we will get 125 kilohertz. Now this speed is less than the 200 kilohertz per the 200 kilohertz that we need. The less than this is less than 200 kilohertz that we need for more accuracy, basically. So then we have our AD mux register here. We are giving it the value 0xC0. Again, we will simply convert that value into binary and give it to the register, the AD max register here. This will using this register, we will simply just give it a reference value to compare it to get our value here. So the bit 76 of this register is the reference voltage here, and here we are using the internal voltage, which is 2.56 volts here, and then our ADC lower and ADC higher bit, we are giving it a 0 here, and in the last 4 bits we are giving it 0 0 0 0, and which will simply just mean to turn the ADC 0 channel on, which we will connect our potentiometer to, and we will simply just change the potentiometer value here to just simply change the other value that we are given. Then we are simply initializing our LCD here using the LCD 8 init function, and after that we are just simply putting a loop, a while one, which will go on like forever. Now this will work until there is an interrupt or the a condition is met, basically. So then in here we will convert our values from analog to digital, basically. So we will set our ADSC, its bit 6 to 1. Now what this will do, it will start the conversion and basically convert our analog value that we are getting from the potentiometer and convert it to digital value that we can then display. After that, we have this other while function here, and it will just simply wait for this function to complete, and then it will break out from the while. Now what it does is it basically gets the ADIF flag here, the interrupt flag that we have here, its fourth bit, and it just checks until it gets to 1. When it gets to 1, this condition will be met, and it will just break out from the loop here. After that, we have this ADCSRA. This will just simply clear our interrupt flag by writing 1 to it. When we will write 1 to it, it will just simply clear our interrupt flag here. After that, we have this unsigned int x here. We are storing some value here. What it is basically doing is it is just reading the value of the lower bits and the higher bits, and it is just simply uh, saving those values, and it is shifting values by 8, and then it is storing those values into the x value that we have here. After that, we have this ITOA function. Now this basically what it basically does is it converts the integer values into string values. We will have some integer value in this x, and it will check for the base. It has the base 10 here, then it will convert it into string here based on the base 10 decimal system. After that, we will just simply set our cursor on our LCD. We will simply display this ADC colon text on our LCD where our cursor is set, and then we will simply display our string value on our LCD. After that, we will just simply put some space in there, and then we will just simply put 500 millisecond display uh, for the conversion. Now let's move on to our Proteus, and I'll show a simulation there. So this is our Proteus. We are just simply I just simply connected all these port all these pins to my LCD. I'm using the LM016L module of the LCD here. My port B is my data port here, which will be displaying the data, and port C is enabling, and the RS pin is connected right here. And then we simply connect our VDD to our positive DC here, and VSS and RW to ground. And we have simply connected a potentiometer of 10K here. Now here we can see that our ARF is connected to ARF. This is basically the internal voltage, and our VCC has 5 volts here. Now here we can see that port F right here, uh, this port F is our ADC port. We can see that it is starting from ADC 0 to ADC 7, and we have I've just simply connected a potentiometer here. I'm giving it 5 volt, which is basically connected from here, and then we have ground, and the middle pin is connected to is ADC 0 pin, AD 0 pin here, the first pin. And we will see that when I run the simulation, you can see that it is displaying some data here. It is displaying our ADC value here that it is getting from here, and I can just simply turn it up, and we can see that it is giving 1023, which is the maximum value this ADC can give, and I can lower the value as well. Now it depends on how smooth the potentiometer is, how slowly it changes the values. It will basically change our values on the display here as well. If we have a potentiometer that can give more than these steps, then we can get more values out there. So this was basically our lab 10's task 2, and thank you for watching the video.